we are discussing linear viscoelastic response of complex materials, and this is the overall scheme which we are following. After looking at some of the introductory concepts, we saw in detail the idea of a relaxation process, because that is fundamental to the viscoelasticity, and we of course always said that real material will have a collection of relaxation processes. And of course, later on in the course, when we look at real data for several material systems, we will try to identify based on the rheological response what is the relaxation process. And just to understand the viscoelasticity and overall development of several material functions, we said we will look at Maxwell model closely. And in today's class, we will finish up with looking at oscillatory shear, which forms the backbone of rheological analysis for viscoelastic materials. And just to remind us, this is the framework we have been using. We said that we will need to define the class of response. So, right now what we are discussing is linear viscoelastic response. We will look at material functions. So far we have defined material functions like viscosity, and we have defined relaxation modulus. Today we will define material functions which are related to oscillatory shear. And of course, we are continuing with Maxwell model as far as a simple model for doing this is concerned. And so, in the last class we had discussed the Maxwell model, and this is basically, it incorporates both viscous as well as elastic contributions, and lambda is the relaxation time which incorporates whether the material will have a predominantly viscous response or an elastic response. So, with this we had also seen that the stress relaxation modulus for a Maxwell model was an exponential function, and how fast the exponential decay is depends on the relaxation time. And so, for fluid like materials relaxation time is very small, and therefore decay is instantaneous, and these materials end up being dissipative, while solid like materials have very large relaxation time and therefore no decay and no dissipation. So, with this we had defined the material function relaxation modulus, and what we can also do is to use this relaxation model to recast the Maxwell model in an integral form. So, given that any differential equation, in this case Maxwell model, can be recast into the integral form, for example using integrating factor or any such method, we can try to simplify this, and by that what we can do is write an integral form of Maxwell model. In fact, in general in rheological analysis, we generally talk of two types of models. One is a rate type model. So, this is an example of a rate type model. Because we incorporate rates of different quantities, and so it is called a rate type model, and then same model can be expressed as the stress at present time, which is an integral of all past deformations, and we saw that in case of Maxwell model, this can be written as the following. So, this is the integral gamma dot yx, and this gamma dot yx is of course at time t prime also. So, any t prime is the dummy integrating variable. So, that goes from any time in the past to present time, and so this is the integral model. So, several models have a rate type expression, or they will have an integral expression, and depending on the convenience we can use either of these, and we will see later on for example that we will to look at, let us say, normal stress differences in complex materials, we can have what is called a convected Maxwell model, in which case rather than using the normal rate we will use convected rate, and that will become an objective and frame invariant model which can be used for arbitrarily large deformations, and in that case the convected model will be the rate type model, and then similarly there is an equivalent which is called large rubber like liquid model. So both of these models are again same, but one of them is written as a differential model or a rate type model, and the other one is written as an integral. So this is also called as a differential model. And we can quickly see this as the incremental deformation in a small time window dt prime, in a small time window dt prime. And this of course is the weighting factor. And we had seen that this weighting factor is large for times which are not so distant, and when time is much more distant in the past, then this weighting factor falls off to 0 and it is an exponential function. So with this review of Maxwell model and its various versions, now we can look at the next probe of rheological response, which is oscillatory shear. So in case of oscillatory shear, we impose either a strain or a strain rate or a stress which is a sinusoidal function. So in general you could have any of the different types of strains, and in this case I have used the notation which is valid for a cone and plate geometry, which is used quite often for rheometry. And in this case what we have is a cone and a plate, and fluid is in between, and the cone is, let us say, rotated. So therefore this direction is phi, the rotation, and the shear direction is theta. So we use spherical coordinates to describe this point, with this as the origin and this going out is the radial direction, and then the angle with respect to this axis is theta. So theta is equal to pi by 2 is which surface? Theta is equal to pi by 2 is the bottom plate, right. Theta is 0 is the shaft, and theta is equal to pi by 2, and of course phi goes from 0 to 2 pi. So this is the, so therefore in this case we have only v phi, and it is a function of r and theta, because as you go radially outward the velocity will be higher and higher, and it is a function of theta also, because theta is equal to pi by 2, which is the bottom plate, fluid will not be moving, and theta is equal to pi by 2 minus theta naught. Let us say if this angle is theta naught, then we have these two boundary condition, theta is equal to pi by 2, v phi is 0, and theta is equal to pi by 2 minus theta naught, v phi will be equal to w r, where w is the rotation rate of the top cone, right.
Phi will vary 0 to 2 pi.
Yes, phi will be 0 to 2 pi, theta will be 0 to pi, right, the usual spherical coordinates. So therefore theta goes from 0 to pi, right. What is your doubt?
Previously you were telling that phi will vary 0 to pi.
No, phi will vary 0 to 2 pi, yeah, theta will vary from 0 to pi. So therefore you can see that theta phi are the two components, that is the shear component. This is again an example of shear flow, and theta phi will be the component which is non-zero, while all the other components which are r, theta, theta, phi or phi r, all those components we will find them to be 0. So therefore in such a situation we will have either gamma theta phi, gamma dot theta phi, or tau theta phi as the quantities of interest. So any of these could be controlled and varied sinusoidally. So, if we have the top cone oscillating, basically we are doing this, or we could say that we will control the torque which is there on the top cone, and we can say that it goes to maximum, then it reverses, goes to the negative maximum, and then again goes like this. So, that is oscillatory shear. And so, what we will look at initially is, let us say, a strain, imposing a strain which is an oscillatory strain. So, now the experimental time scale is being manipulated with frequency. If we apply the strain very quickly, then we are giving material very less time to respond to the mechanical stimulus. If we do the experiment extremely slowly, then we are giving the material enough time to respond. So, therefore, frequency which is inverse of time is what is being manipulated in this case. So, we would expect that what is the long term behavior will be observed when you have very low frequency being imposed on the material, or very short time response of the material is equivalent to saying that I am doing the experiments at very large frequencies.
This gamma theta phi is strain rate?
No, strain.
So, dimensionality will be?
This is right, amplitude is there.
That is strain rate amplitude.
No, no, this is gamma naught to indicate it is constant, not gamma dot. So, if at all we maintain strain rate, then it will be gamma dot theta phi equal to gamma dot naught theta phi. I mean, so naught we are just saying it is a constant value, it is an amplitude of the strain which is being imposed on the material. And so, given that we are imposing a sinusoidal strain on the material, the general stress response would also be a sinusoidal function, and in general that is will be a sine function, most generally any function, and it may or may not be in phase with the input. For example, if we have a Hookean elastic solid, then we know that if strain itself is a sin omega t, then stress also will be sin omega t, because wherever strain is maximum, stress will be maximum. So, for a Hookean solid, we know that tau theta phi will be actually some amplitude and then sin omega t itself, because it has to be in phase with. What about Newtonian fluid? For Newtonian fluid,
It will same.
Newtonian fluid, how will it be same?
Strain rate.
Yeah, it is proportional to strain rate, right. In case of Hookean solid, the stress is in phase with strain, but for a Newtonian fluid it is proportional to strain rate, and strain rate from this is gamma dot theta phi into omega gamma theta phi naught cos omega t, right, that is the strain rate. So, which is just a derivative, and we again should remind ourselves that the transformation from going from strain to strain rate we are doing by simple time derivative, because we are looking at linear response, because we are looking at small deformations. In general, strain derivative, partial derivative of strain is not strain rate, only because we are working with small deformation we can do this transformation easily from strain to strain rate. And so, this is the strain rate, and then therefore, we would expect for a Newtonian fluid we would expect the stress to be some amplitude into cos omega t, right, because stress is proportional to strain rate. And so, therefore, we can see that for a Newtonian fluid, strain and stress are completely out of phase. So, therefore, this delta is pi by 2, while for Hookean solid the stress and strain rate strain and stress are in phase, therefore, this delta is 0. So, therefore, we have written a general statement that for any linear response of the system, in which way this is linear when I write these two together, where is the assumption of linear being made when I?
For small deformation.
Yes, small deformation. So, when I write this expression, can you make out that it is linear response? Is it possible for you to see, as soon as I say okay, this is the strain response, and if I write this as an expression for stress, the only thing that we have said is most generally it could be any phase lag, but we are also saying that the response will be at the same frequency as that of input. So, that is inherently only possible for small deformations. Only for linear systems, the stimulating whatever frequency is being used to provide a stimulus, the output is also at the same frequency. Otherwise, generally we will observe higher harmonics for a nonlinear system response. So, therefore, as soon as I have written this, it is also assuming linear response. Within linear response, this is a completely general expression. And so, now of course, this only says that the stress is expected to be also a sinusoidal function, and if we were to solve this for Maxwell model, then we need to substitute this in the Maxwell equation and then solve it. So, what we would need to do is just tau Ix plus lambda del tau Ix by del t is equal to eta omega gamma theta phi naught cos omega t, right, because that is what is gamma dot theta phi. And so, this simple ordinary differential equation needs to be solved, and we can then get tau Ix as a function of time, which is this solution we are seeking. Okay. So, generally what we do is the following, we will solve for tau theta phi, and then based on those we will define material functions. So, let me first show what is the solution for Maxwell model, and then we will come back and look at the solution. So, tau Ix, if you were to solve this equation, you can get it in terms of the prefactor which I have, gamma theta phi naught g omega squared lambda squared 1 plus omega squared lambda squared sin omega t plus g omega lambda 1 plus omega squared lambda square cos omega t, right. So, this is the overall solution according to Maxwell model. Any generic viscoelastic material will give this response, but according to this now there is a specific response, and what is the phase lag?
Pi by 2.
Is it why is it pi by 2?
We can convert cos theta in terms of cos.
No, it is not pi by 2, right. The overall phase of tau Ix will depend on how significant these quantities are. What this is saying is the overall stress response of the Maxwell model has some part which is in phase with the strain and some part which is out of phase. If let us say this term was 0, then we can say that it is completely in phase. If this term was 0, then we can say it is completely out of phase. So, by definition, given that Maxwell model is a model of viscoelasticity, we have a phase lag which is between 0 to pi by 2, and only at the two extremes of completely viscous response or completely elastic response it will go to 0 or pi by 2. So, therefore, in fact you can if you see there you can expand this, right, sine function as sin omega t cos delta plus cos omega t sin delta. So, in fact can you see that these are in fact sin delta and cos delta, right.
Yes.
So, this is cos delta and this is sin delta. So, what is tan delta? One by omega lambda, right. So, that is tan delta according to, so that is the phase lag according to Maxwell model, and so the phase lag changes when you change the frequency of the material. Now, does it make sense that when frequency is very small, what is delta? when frequency is very small, this is infinity, so therefore pi by 2, right. When frequency is very small, we are allowing material enough time to respond, therefore all relaxation processes can happen, material will show dissipative response and viscous response. If we apply very high frequency, we are not giving material enough time to respond, because we are providing the mechanical stimulus very fast. So then many relaxation processes will appear to be frozen, and therefore they will contribute elastically, and therefore material will be elastic, or in other words phase lag will be 0, right. So that is how the Maxwell model can actually show the responses, which is both viscous and elastic depending on what is the frequency or depending on what is the relaxation time, right. This is also another thing we have always been saying, that you cannot isolation look at only the experimental time scale, it is always with the comparison between experimental time scale and material time scale. So if the relaxation time of the material is already large to begin with, then what happens is even at low frequencies itself, I will have to go to very low frequencies to see some viscous response, otherwise I will automatically start seeing elastic response, because lambda is large, tan delta will already tend to 0. Other way, if lambda is very small, then I will have to go to very high frequency to see any elastic contribution, otherwise since lambda is very small, tan delta will always be close to infinity or pi by 2 as the phase lag. So therefore Maxwell model and these two terms actually contain what is the viscous and elastic response of the material, and so what we do is we choose to use these terms to define the two material functions. So we say that the part of, and you can see this is strain and this whole thing is stress, so these factors are units of stress because the left hand side is stress. So therefore this is analogous to a modulus, stress is overall proportional to strain, right, of course with a time dependent function, because the strain itself is also a time dependent function, and therefore we say that this is a storage modulus or elastic modulus and the quantity which is the second modulus, what will it be? If you have to guess, what will be its name? Viscous modulus or loss modulus it is called. So we again storage versus loss, elastic versus viscous. Because if this modulus were to be 0, then we know we have a Hookean solid, because stress and strain are completely in phase. If this term is 0, elastic modulus is 0, then we have a viscous fluid, and so these are therefore called these are two new material functions that we have specified, and we will indicate this as G prime and this as G double prime. So most common reporting of rheological properties is in terms of G prime, G double prime. Why are we using G? Are you saying what is this G or what is this G?
Yeah,
That G is eta by lambda, right, our Maxwell model parameter. We can express it in terms of eta and lambda, or we can express it in terms of, so that is the Maxwell model parameter. So
it is dimensionless term or
which one?
G?
You please check what is dimensions on eta?
Same as viscosity.
Viscosity, so Pascal second, then dimension on lambda is second, so therefore it is dimensions of Pascal, it is modulus, right. So therefore since it is a dimension will be yeah, we are using the symbol G to indicate that we are working with shear. So in fact some experiments and especially for solid viscoelastic materials you can also do tension easily. So then in that case many times they will refer to E prime and E double prime. So this is a normally followed convention that E, capital E as a symbol is used for tensile mode of deformation. So you can take a rod and then you can do a tensile oscillatory experiment. So, then you will have an elastic modulus and again loss modulus or viscous modulus, and we use G prime and G double prime for generally indicating shear. So, most of the times whenever materials are fluid like, we would do shear response. And these are again material functions because its functions of frequency. So, given that we have storage and loss modulus for a material, we can find out what is its overall viscoelastic response, because in the end what we have done is we have, for the governing equation of viscoelasticity, we have substituted what is the mechanical stimulus and then solved and got this response. So, this G prime and G double prime contain information about what is the model like. And so, in general we can write T y x as gamma theta phi naught G prime which is a function of omega sin omega t plus G double prime which is also function of omega cos omega t. And we also define one more material function which is given as G double prime by G prime, which is either called loss tangent or tan delta. So, sometimes it is referred to as loss tangent or just tan delta itself. So, these are the three material functions. So, naturally when I am looking at a new material system and when I do a shear experiment in cone and plate by applying sinusoidal deformation, I can obtain these three material functions, and then I will need to figure out how is the response compared to what I expected. So, for a Maxwell, if a material meets is very similar to Maxwell model, then I will get a response which is exactly given by these. And if you look at the overall response, it is always helpful, as I have been saying in rheologics, to look at terminal response. So, let us first look at terminal of what if frequency is very small. So, what is the response? So, if frequency is very small, then what is G prime? It is I mean when frequency is very small, yes, but rather than just saying 0, what you can see is if frequency is small, then compared to 1 and this 1 can be taken and you can ignore this. So, therefore, G prime is proportional to omega squared, right, that is a terminal response. So, as viscosity tends to 0, you would see that G prime and omega relationship will be a power law. And what about G double prime? It will be proportional to omega, right, because again you can ignore. Now, if you go to the higher frequency on the other hand, then what happens to G prime? If omega is very large, then you can ignore 1 and therefore G prime becomes constant, and G double prime is inversely proportional to omega, right. So, this is the terminal response. Does it make sense from what we discussed in terms of fluid like and solid like response? Do any 4 of these make sense to you, saying that we have said that if I do very high frequency, then I am perturbing the material very fast and therefore I will see elastic contributions and largely material will behave elastically. So, therefore I would expect that elastic modulus to be a constant, okay, and under those conditions whatever little loss is there, it is going to be inversely proportional to omega. What happens is, through many elastic materials like steel, we ignore this part because it is not very relevant and it is also very small. So, for all practical applications we say that we will ignore this. Similarly, what about this? Does it make sense, any of these? At low frequencies we are giving material enough time so that all the viscous contribution is there, all the relaxation processes can take place, purely dissipative response. So, does it make sense that G double prime is proportional to omega? What is G double prime? If you just look at this, it is eta times omega, right. In fact, if you write the expression, it is eta times omega.
But if omega is constant, then all the parameters will be constant.
Yes, of course, because they are functions of frequency only. The idea of varying omega is because we would like to explore the viscoelasticity of the material. When you keep omega constant, then you are saying that only that frequency of interest. So, generally we vary omega to do the experiment. For example, when we are doing a steady shear experiment, we vary the strain rate,
Yes.
right, and therefore viscosity is function of strain rate. So, in this case what we vary is frequency, and in general let us say we are developing a gel for cold cream applications. So, then we would like to know how would it respond at low frequencies, because that is when it will be in the bottle, or when I take out on the hand it will remain almost stationary. So, with little shear how does it respond, but then when I start spreading it or rubbing it, then it is very short time scales, so which means high frequency. So, in general it is a good idea for me to put the material in rheometer and then look at whole frequency range as possible. So, we can do the strain rate also, but it is only a steady test, and we saw that whenever we do a steady test, we cannot get overall idea about viscoelasticity in the material. It gives us only partial information, because we are only looking at the steady state the structure of the material, and therefore it is only steady state response. By doing oscillatory shear, we are in fact saying that we will impose a time dependent deformation and therefore look at time dependent response of the material. So, does this make sense that G double prime is eta omega? So, what we will be able to visualize is